So, what in the world does a car engine have in common with a star? Well, the answer is thermodynamics, the science of energy itself. Today, we're going to break down the fundamental rules, starting with the biggest challenge of all. How do you even begin to measure something as wildly chaotic as a thermodynamic system?
Here's a quick look at where we're headed. We're going to start in a world of pure chaos and see how physicists manage to bring order to it. Then we'll check out the dashboard they use to read these systems, uncover the one rule that connects everything, and finally, see how these perfect, almost imaginary models help us engineer the real world. All right, let's just dive right in. I want you to picture a simple box full of gas. Seems easy enough, right? But inside, you've got trillions of particles, all zipping around with their own speeds in their own directions. It's just pure, absolute chaos. So how on earth could you describe a system like that with just a few simple numbers? I mean, it seems totally impossible. Yeah, trying to track every single one of those particles is a non-starter. So instead of trying to calculate the chaos, physicists have this much more elegant trick. They just wait. You see, if you leave a chaotic system all by itself, it will naturally settle down into a stable, balanced state. Just like you see here, the mess on the left gives way to the nice, orderly system on the right. This is what we call thermodynamic equilibrium. And it's only in this calm, balanced state that things like pressure and temperature become uniform enough for us to actually measure them. Okay, so our system is stable, it's measurable. What do we actually look at? Well, think of it like your car's dashboard. It doesn't tell you what every single part is doing. It just gives you a few key readings that tell you everything you really need to know about the car's condition. So these key readings on our thermodynamic dashboard are called state variables. And for a simple gas, you really only need four things. There's pressure, that's the force the gas is pushing with. Temperature, basically how much energy the particles have. Volume, how much space it all takes up. And of course, mass, how much stuff is actually in there. You get those four numbers and you have a complete snapshot of the system's state. It's that simple. But here's where it gets kind of fascinating. What do you think would happen to these measurements if we just, cut our system right in half? Would they all change? Well, it turns out they fall into two very different groups. You have your extensive variables, like volume and mass. These guys scale with the size of the system. Then you have intensive variables, like pressure and temperature. And these stay exactly the same no matter how much of the gas you're looking at. And this slide shows a really clever little thought experiment called the partition test. You've got your box of gas, it's in perfect equilibrium. Now just imagine you could magically snap a divider right down the middle. Well, the volume on each side is now V over 2, and the mass is M over 2. They're cut in half, so they are extensive. But what about the pressure or the temperature? They stay exactly the same in each half. They're intensive. It's a brilliant way to sort these properties out. So we have this dashboard of variables. That's great. But are they really independent? I mean, can you just crank up the pressure without changing the temperature? Or is there some kind of secret connection between them all? Well, as it turns out, they are not even close to being independent. For any given amount of gas, these variables are all locked together by a fundamental law of physics. If you know two of them, the third one is completely fixed. You don't get a choice. And honestly, this gear analogy is the absolute perfect way to picture this. It's like pressure, volume, and temperature are all connected. If you try to turn one gear, like pressure, the other two are forced to turn with it. They are mechanically linked by something called an equation of state. Now, for a lot of gases, we can use the famous ideal gas law, PV equals mu RT. That mu is just the amount of gas, and R is a constant. And this one simple formula ties all of our state variables together. Let's make this real for a second. Let's say we have 1 mole of gas, that's our mu, at about room temperature, so 300 Kelvin, and we stick it in a container of a certain size. The moment we define those values, bam, the equation of state locks the pressure in. It has to be 99.7 kilopascals. You can't change it. They're all connected. So we figured out how to describe a system that's just sitting there, peacefully, in equilibrium. But the whole reason we study thermodynamics is to understand change, like the stuff happening inside an engine. So what happens when we try to go from one state to another? And this is where we hit a huge wall. If you change the system too fast, like you just slam a piston down, you throw the whole thing out of equilibrium. The molecules all bunch up, the pressure and temperature go all over the place, and you're right back in chaos. And in that chaotic moment, our dashboard goes dark. Our state variables don't mean anything anymore, and our super powerful equation of state, it completely breaks down. So how can we possibly analyze change if the very act of changing breaks all of our tools? The solution is this beautiful theoretical idea called a quasi-static process. Imagine that instead of slamming the piston, you have a pile of sand on top of it, and you remove one single grain at a time. Each little step is so tiny, so infinitesimally small, that the system has time to adjust and rebalance itself. It's an idealized, infinitely slow journey that moves through a whole sequence of equilibrium states, which lets us use our equations every single step of the way.
This really powerful idea of a slow, controlled, quasi-static path, it gives us a whole new framework for analyzing change. And by controlling different variables during this slow process, we can actually define 4 fundamental ideal paths, or you could call them operating modes, for any thermodynamic system. We basically classify these ideal processes based on which one of our state variables we decide to lock down and hold constant during the change. Each one has its own special name, and it represents a totally unique way to get from one state to another. So first up, we have an isothermal process. And the name kind of gives it away. Iso means same, and thermal is about heat. So this is a process where the temperature is held perfectly constant. The way you can picture this is by putting our system in this huge heat reservoir that can give or take as much heat as needed to keep that temperature dial from budging. A completely different path is the isobaric process. Again, iso for same, and baric is about pressure. Think barometer. In this case, the pressure is what's held constant. And this slide shows a great way to imagine it. You just have a piston with a fixed weight on top. So even if the gas expands or contracts, the pressure it's under never, ever changes. Okay, our third path is the isochoric process. Iso comes from a Greek word meaning space. So, yep, this is a constant volume process. Imagine the piston is just welded shut. It can't move. Now, if you pump a bunch of heat into this thing, the molecules are going to go nuts. The temperature and pressure will just skyrocket, but the volume is totally, completely fixed. And our fourth and final ideal path is the adiabatic process. Now, this one's fundamentally different. We're not holding PV or T constant. Instead, we're cutting the system off completely by wrapping it in perfect insulation. Absolutely no heat can get in or out. In this setup, the only way to change the system's internal energy is to physically do work on it, like compressing the gas with the piston. So, okay, we have these 4 perfect, idealized, infinitely slow processes. But what's the point? I mean, nothing in the real world is infinitely slow or perfectly insulated. So why do these theoretical models matter at all for practical real-world engineering? Well, here they are, our 4 ideal building blocks all laid out. Each one is defined by just a single, powerful constraint. You either lock the temperature, or the pressure, or the volume, or you completely stop the flow of heat. Think of these as the fundamental moves in the language of thermodynamics. And by combining them, engineers can describe and build incredibly complex cycles, like the ones in a power plant, or even your refrigerator. And this graph right here, this is the payoff. The smooth blue line is our perfect, ideal path, the one that's super easy to calculate. The jagged orange line, well, that's the messy reality of what actually happens inside a real engine. But just look at how closely the real process can hug that ideal curve. As long as a real-world process is slow enough, our idealized model is a fantastic approximation. It means we get to use the clean, simple math of these perfect paths to design and understand the messy, complex engines that power our entire world. So, let's bring this all home. We start with total chaos, but we find order in equilibrium. We measure that order with state variables, which, it turns out, are all linked by the equation of state. Then, to understand change, we use the clever idea of an idealized quasi-static path. And that really is the main takeaway. We design for the ideal in order to manage the real. By understanding these perfect models, we get the power to actually engineer our world, which, it leads to one last really interesting question. If this whole framework is so good at helping us understand engines and stars, could we use the same principles of equilibrium, state, and ideal change to better understand other complex systems, like our economies, or maybe even our planet's climate?